Thanks everyone for joining us in these interesting times. We've got George Malliaras is joining us from the UK today, this morning for George, of course, and this afternoon for most of us. So just a brief introduction. George is the Prince Philip Professor of Technology at the University of Cambridge. He's had several other positions before moving to Cambridge, and during those his research has been recognised with awards from the New York Academy of Sciences, the National Science Foundation in the US, and DuPont. George is a fellow of the Materials Research Society and of the Royal Society of Chemistry, and a deputy editor of Science Advances. So I think most of you online will know George and will have met him. His contributions to the field of organic electronics are very well known and indeed legendary. His fundamental insights into how these systems like organic conducting polymers actually work has enabled effective implementation of these materials in a number of fields, including medical bionics and in energy conversion, both of course areas that are of great interest to those of us in ACES, in our ARC Centre of Excellence. So George has had that demonstrated record of being able to take those fundamental advances and use them in real applications. And so it's a real privilege for us to be able to share a bit of time with George and some of his insights into these materials and applications of them. And I'll just introduce George and thank him very much for joining us this morning. Thanks, George.
Gordon, thank you very much for the kind introduction. Thank you for the invitation. It's a great pleasure. The privilege is mine. We're following along your footsteps. And this is a community that you have championed, and we're just delighted that you plowed the road for us to learn a lot about this field and be able to translate some of that into devices. So I want to spend the next 25 minutes or so, 25 minutes on exploring an old question, whether conducting polymer electrodes are capacitive or Faradaic. And I'll explain why we need a new take on this. So as Gordon mentioned, there are many applications for these materials. In bioelectronics, what you call bionics, is the application where you try to interface with living systems in order to understand some aspects of biology and to be able to deliver treatment. In energy devices for energy storage, for energy generation, such as in photovoltaics, as well as in displays, electrochromic displays. The work shown here, where you make pixels that change color upon the application of a voltage. The performance of this material has been described with the words capacitive or Faradaic. And before I start, I want to lay down some definitions, make sure everybody is on the same page. This language evolved from metal electrodes in electrolytes. And capacitive is meant to define the state where you apply a potential between two electrodes immersed in an electrolyte. And the next thing that happens is ions will come and butt against the electrodes and form a double layer between the electronic charge inside the electrode here and the first layer of ionic charge that just sits on the electrode. There is a polarization here. This looks like a small capacitor, and the same thing happens at the other side. If you were to look at current voltage characteristics with cyclic voltammetry, which is a technique that's very often used to characterize these interfaces, you get the behavior that looks like a box. And what this situation is characterized by is that you can store charge near the electrodes, and the current that flows into the system is transient only. So current only flows when the ions move and butt against the electrode, and then it stops. Contrast this with the case of Faradaic response, where species in the electrolyte will exchange electronic charge with the electrode. This means that here comes a molecule, or it could be an ion, that either gives or picks up an electron from the electrode itself, which causes a steady state current to flow, provided that the opposite electrode is also Faradaic and can complete the circuit by injecting or extracting the opposite electronic charge. The current voltage characteristics on the CV have these characteristic peaks that are associated with the so-called redox process, the process of exchanging charge at the electrode. And this is an electrode that obviously transfers charge to the electrolyte. And again, there is steady state current. Now, why do we care about this? We care about this because different applications require different optimization of the system to work in either of these two extreme limits. It is known that Faradaic electrodes, the exchange of charge that happens between the electrode and species in the electrolyte leads to downstream chemical reactions. And that is not desirable in the brain. For example, if you're making deep brain stimulation electrodes, you do not want Faradaic reactions. You want to avoid those because you don't want to alter the chemistry of the brain. On the other hand, if you're after electrocatalysis, where these chemical reactions is what you're after, you want to optimize your system so that it works closer to the Faradaic limit. Now, this was the case for simple metal electrodes. When you slap a semiconducting or a conducting polymer, a conjugated polymer on the metal, then the situation becomes much more complex. This is a CV cyclic voltammogram of a polymer, conjugated polymer on a metal surface. And you see that it has peaks that you would assign to a Faradaic response, but also has this plateau here that you would be tempted to assign to a capacitive response. So here opinions are divided. I think the majority of people will tell you that you have a mixed response, a pseudo-capacitance. There are different terms that are used to imply that you have a bit of both, a character that is both Faradaic and capacitive. But this is not necessarily, there's not necessarily consensus. Here's one example where, from a review paper, where it states that the controversial capacity-like plateau, this red area here, which generally appears in voltammograms of conducting polymers, can be shown to refer to a Faradaic process. So according to this school of thought, everything is Faradaic, there's nothing capacitive. My view, which will become clear as we go along, is that cyclic voltammograms are a particularly bad way to study these systems because they reflect the outcome of a cascade of processes. There are too many things that happen here. And what you measure, the current, is an outcome of at least 3 processes. And it's not the best indicator for device operation. You need to break it down a bit more in order to decide whether you have capacitive or Faradaic. Now, going a bit more over the literature, if you look into the modeling that has been done for the electrochemical characteristics of these systems by using equivalent circuits, you will notice again there's no consensus. There are all kinds of different circuits that are being used, often with nonlinear elements, such as this constant phase element or this Warburg element here, that seem to imply Faradaic processes. There is also, if you delve a little bit more into the language, the motion of ions in these films is often termed as diffusion. And whether there is drift, whether there is a field inside these polymers and ions can respond to that is something that is debated. So there is scope for taking a new look at this old problem. And the material that we've been working with is called P.PSS. I'm sure it needs no introduction in this community. It's a commercially available conducting polymer. It consists of P. which is a polythiophene, which is degeneratively doped with polystyrene sulfonate to be P-type. And the holes are compensated with sulfonate ions on the PSS. I'll show you the structure in the following slide. There is mounting evidence over the last decade that, that this system shows purely capacitive behavior. And to the best of my knowledge, it is the only system that has been identified to show absolute textbook example capacitive behavior. So it makes sense to look into this, why this behavior arises. And then ask the question, is this the only one in the world, or is it more of the example that proves the rule, the exception that proves the rule? So let me review the evidence. From electrochemical spectroscopy, we've seen that it behaves in an ideal fashion. From so-called moving front measurements, we can look at the motion of ions in this field and show that there is an electric field inside the film during electrochemical doping processes. And then from device work, we can understand fairly sophisticated device behaviors by a very simple capacitive model. So let me go through the data really quickly. This is impedance spectroscopy that we've done together with Dave Martin when he was on sabbatical with us. I'm sure you know Dave, he's been one of the pillars of this community. We made electrodes with different shapes, different sizes, coated with P. films of different thickness, and used P.PSS that was deposited either electrochemically or by spin coating. This was very laborious, very painstaking work. For every electrode that we made, we cross-sectioned it using FIB, focus time beam, and we very carefully accounted for edge effects, making sure that we know the exact volume of the film and that the films look to be of very high quality. So literally hundreds of impedance spectra, hundreds of cross-section. And all of this data can be fit with a very simple model where we can account for the electrochemical impedance of these materials by a resistor in series with a capacitor. So if you plot the impedance of a resistor in series with a capacitor, you get this equation. If you divide Z by R and plot the frequency multiplied by this factor, all the curves collapse to this universal one. And here I include characteristic examples of curves with different dimensions of the P. film, different thicknesses of the P. film, different, let me see, I cannot see the label because the picture window is here. Okay, different dimensions, thicknesses, different electrolyte strengths, and they all collapse to the same curve. Very strong evidence that this is a capacitive response. If you analyze the data, then you get that the capacitance of the film is linear, scales linearly to the volume of the film, as you would expect from a textbook volumetric capacitor. This means that ions from the electrolyte get inside the P. film and distribute uniformly throughout this volume down to voxels of 10 cubic microns. The resistance scales with the perimeter of the electrode as expected due to the distribution of the electric field. There is an old paper shown here, published in '66, that postulates that if you put an electrode in an electrolyte, any electrode, the field will be located around, will peak around its perimeter. So if you have to describe a textbook capacitor, volumetric capacitor, this is how the data would look like. How do we understand this? We can understand using a toy model, starting from a Helmholtz model of capacitor, where you have an impenetrable electrode with ions butting against it. You have a capacitance that is, if you normalize it per unit area of the electrode, would depend on some dielectric constants, and then a distance, which is the center of the ion to the electrode surface, so that would reflect the solvation sphere of the ion. And uniformly, this has values across many different flat metal electrodes of the order of 1 to 10 microfarad per square centimeter. Now, in a three-dimensional electrode like P.PSS, you come up with the following model. You have PSS chains that carry the sulfonate ions, shown here. On the PSS, along the PSS chains, we have the P-dot chains that are polymerized side by side and would have the holes that are obviously free to move and jump from one chain to the other, giving rise to macroscopic conductivity. Then what happens if you inject a cation from the electrolyte? It will come and compensate the sulfonate anion, while a hole from the P-dot adjacent P-dot chain that was compensating this anion would be extracted through a metal electrode to give you charge neutrality. So what you do is you form a little capacitor here in a similar vein as the Helmholtz capacitor shown here. And these are distributed throughout the volume. So what you need to know is what would be the distance between these ions, this and the next one, which you can infer from the doping density of P.PSS. And then you can come up with a very simple toy model where you slice the volume into thin slices and account for how many capacitors you can have per unit volume. And this is a back of the envelope calculation. And you can extract the volumetric capacitance of P.PSS to be equal to the capacitance of a double layer, which again has this fixed value of 1 to 10 farad per square centimeter, divided by the distance between the doping sites. So if you put the numbers down, again, 1 to 10 microfarad per square centimeter, you end up getting a capacitance per unit volume for P-dot that should be between 6 and 60 farad per cubic centimeter. What we measured here, and I failed to mention, is 40. The slope here gives you 40 farad per cubic centimeter, which is within this range. So a very simple back of the envelope calculation gives you a quantitative prediction of what the capacitance should be. And it also tells you that if you can densify the system, if you can get rid of the P-dot, you can access capacitances up to 200 farad per cubic centimeter. And indeed, today, we have materials in our hands that have capacitances up to this value. You can do it better. You can be a bit more rigorous by using numerical modeling. This is work done in Magnus Berggren's group in Sweden, where they can reproduce the CVs of P-dot cyclic voltammograms by looking into a phase-separated system of having PSS, which is an ion conducting phase, with P-dot, which is a hole conducting phase. And they can also get this 40 farad per cubic centimeter. Moreover, they also show that sometimes peaks can appear in the CVs of these materials, despite the fact that they're purely capacitive. So the lesson here, this is a very important paper. It shows that peaks in the CV do not necessarily have a Faradaic origin, but they can be because the material has two phases, or because the mobility in the film is electric field dependent, or because there is an injection barrier between the metal electrode and the film. Now, continuing a bit further with evidence of ideal behavior, if you wish, we did this moving front experiment following along the steps of others such as Aoki, Smela, and Inganas, who did this type of measurements. Here we did them in one dimension. So we made a geometry where we have a P dot film, we have a barrier on top, a barrier on the bottom, and we can only inject ions from the side. So as you do that, you have P dot, which is normally doped. It has the fixed sulfonate ions, and then the holes that can move about. And when you inject cations under the influence of an electric field that is applied laterally between the electrolyte and an electrode, then these ions will compensate the sulfonate anions, and holes will be extracted through the gold. So as you do this experiment, you apply a potential, you start injecting cations, they start compensating the anionic charge, holes get extracted, this bit of material gets de-doped, and you have this de-doping front that moves inside the sample. And as it does, it changes the color of the material. So if you just shine light through this sample, you can see a de-doping front spread through the sample. There is a lot of information here. For example, the fact that the plateau here, the top, stays at the same value means that the compensation is complete, and the number of cations that you inject compensates completely the sulfonates throughout the material. It also means that there's no injection barrier for ions, but ions can penetrate the film very quickly, very easily. So you can also get the speed by which ions move. And if you look into a very simple model saying that this is ionic conductivity, this is electronic conductivity, you can get both the mobility of the ions and their density in the film. You can separate the two. This is a time of flight experiment, if you wish. And you end up with values that show that, first of all, cations fully deplete the film during impedance measurements, both because their density is such that they can compensate every anion in the film, but more importantly, they have enough mobility. They can move fast in and out of the material. So when you do your impedance measurements, they can completely deplete and repopulate the sample during a scan of the frequency up to fairly high frequencies. You can model this with drift diffusion simulations, so you get beautiful profiles, the same features that you see in the experiments you can get by a drift diffusion model. So again, fully capacitive type of behavior. The third type of evidence comes from devices that are called organic electrochemical transistors, which have been developed by folks at MIT, Mark Crichton's group at the time back in the 80s. And they were regarded as an electrochemical curiosity. Here you have a polymer between source and drain electrodes. You have a gate electrode in the electrolyte, and you can dope or de-dope the polymer and then measure its conductivity. So it was viewed as a way to study the doping of these films. Later on, electrical engineers got their hands on this and started looking at this as devices, semiconductor devices. And we built a model, which is called the Bernard's model, that explains the behavior of this. I'm not going to go through the details, but it explains how the electrical characteristics of this behave based on very simple processes where ions from the electrolyte go into the film, and then a hole gets extracted and doesn't get replenished, so the material gets de-doped. You can write very simple equations, integrate them, and then you get the behavior of the system. For example, the transconductance, which characterizes the amplification that you get in this transistor. You find that it scales with the thickness of the film, which is unusual for a transistor. It's a characteristic of this volumetric capacitance of P dot. Excuse me. And you can capture this behavior by this simple model. You also can capture the time behavior of these materials. You can understand very basic transistor type of characteristics using a very simple model. Not only that, but this provides a mechanism to classify different materials based on mobilities of electronic charge and volumetric capacitance. And we make this plot where the better materials lie up on this top right corner. And this has guided the synthesis of these materials in the field. And currently there are materials that exceed the performance of P.PSS in these devices. And there are reasons for that that I don't have the time to go over. So I hope this is convincing that P dot acts as an ideal volumetric capacitor. And the question is why, and is it the exception or the rule? So this got us thinking, and 5 minutes and I summarize. Why is this the case? I go back to the early work on light emitting diodes, where these are devices that are today used in flat panel displays, as you all know, where describing the performance of these devices by using an energy level diagram has had tremendous impact in learning how to make these devices better, how to understand their behavior and make them better. So the way we understand light emitting diodes, the single layer device shown here is that you have a metal, another metal electrode sandwiching a polymer layer. You represent the polymer by the highest occupied and lowest unoccupied molecular orbitals, the two metals by their Fermi level. And what this device does, it injects electrons into the LUMO over a small barrier here, holes into the HOMO over a small barrier there. The two carriers drift towards opposite sides, and then they recombine and light gets produced. So once this energy level diagram was put together, then simulations were able to take place to evaluate the different parameters. For example, what is the impact of injection or mobility of different carriers in recombination, as shown here. These are examples of where the recombination takes place, where electrons and holes meet within the device as a function of the ratio of mobilities and different injection barriers at the anode, the cathode. This type of work was of fundamental importance for helping us understand and optimize the the performance of these devices. So what we propose is that we use the same language for electrochemical devices. For electrochemical doping to take place in a semiconducting polymer, take a polythiophene, put it on a metal electrode, immerse it in an electrolyte. If you apply a potential that can bring anions into the film in order to dope it, the following processes happen. Electronic charge, the hole has to be injected from the metal to the polymer. It has to be transported some distance inside the polymer. At the other end, an anion has to be injected from the electrolyte to the polymer, transported over some distance, and then the two can compensate electrostatically each other. So these are the elementary processes. They don't happen necessarily in this order. The order at which they happen takes place is determined through local electric fields and band structure of the material. You can even start putting energy level diagram for these processes together, same as a light emitting diode, and start describing the process. However, so far, what I have described is a purely capacitive process. What I'm telling you is that the electrochemical doping of a polymer is a purely capacitive process. There is no exchange of electronic charge between the polymer and the electrolyte. It's just a compensation effect that forms little capacitors somewhere in this structure. So why do we see peaks and why is there evidence for Faradaic response? I would argue that this is a byproduct, a deviation from this ideal picture. For example, often you have a species in the electrolyte, such as oxygen, whose energy level, the lowest unoccupied molecular orbital in this case, lies low, well within the manifold of highest occupied molecular orbitals of the polymer. So you can have electron transfer reactions now between your polymer electrode and species in the electrolyte. These would be Faradaic reactions. And these have been seen in P.PSS, for example, if you overdope it, if you de-dope it too much, then the Fermi level rises to a level where you can transfer oxygen and this down the road leads to formation of superoxide and peroxide. And P dot is a very efficient way to make peroxide if you optimize the system to do so. You could have a situation where ions cannot penetrate into the film, but rather butt the surface against the surface. And that causes very large electric fields here that will give rise to electrolysis. That's again a non-ideal behavior. It departs from the ideal example I showed you earlier, and it would lead to Faradaic response. So using this framework can be very powerful to understand this phenomena. And there is a clear way forward. We can transfer knowledge on how charges are injected and transported from organic electronics. The field of organic electronics has developed wonderful ways to discuss this phenomena, and we can transport this knowledge to electrochemical systems. We need to develop techniques such as the moving front technique that can isolate elementary processes such as ion injection and transport, and begin to understand the coupling with electronic conductivity and energetics. We need to understand the nature of the charge compensated state, whether it's collapsed, whether it's extended, and to develop an energy level description that supports the engineering of devices. Before we developed that for light emitting diodes, we were cruising blind. We did not know how to optimize the devices. This is the same thing in electrochemical devices today. There is no energy level description, and this is missing, and it would help tremendously when this is developed. So to conclude, the operation of devices using polymer electrolyte interfaces is still being debated, the mechanism of operation. P dot is a shining example that behaves as a textbook volumetric capacitor. You can understand this behavior because charges, whether electronic or ionic, can enter the film without facing any barrier. And there is facile transport of both these carriers in the film. And what I advocate is that applying the device physics that we learned from OLEDs to metal polymer electrolyte devices can be fruitful for understanding and optimizing their operation. So I'd like to thank my group, various collaborators, funding agencies, and thank you very much for your invitation and your attention. I should single out Magnus Berggren, sorry, with whom most of this work was done, and other people. I'm not going to go into details. Thank you very much.
Thank you, George. If anyone's got any questions, you could send those on the chat, or Lauren will moderate any questions for George. But while you're thinking about any questions that you might have, George, so you mentioned about these different phases giving rise to the capacitance effect. So, but obviously at the moment, maybe we do, or maybe you do, but we don't really pay a lot of attention to controlling the size of those phases or the distribution of them. I mean, would that be an important fabrication aspect in terms of controlling capacitance?
Absolutely, yes. Yeah. So with P.dot PSS, you can play a little bit with the trade-off between ionic and electronic transport by using different co-solvents to ripen and extend the P.dot reach phases. That gives you higher electronic transport and decreases somewhat the ionic transport. And we looked into what that does to capacitance and impedance and electrochemical performance and transistor performance in general. Now, better P.dot is not the ideal material for structure properties investigation because you have limited range of modification, if you wish. There can be better model systems where you could, for example, attach different side chains and control the mechanism of ion injection. You can make it so that you block ions completely from entering the film, all the way to the other extreme where you put hydrophilic side chains and you have ion entry from the electrolyte into the film, which is very facile. We have explored the electrochemical characteristics of these materials, and you get a very broad range. You get the difference between night and day when you just change the side chain. Another degree of freedom that has not been looked at all is what happens at the back metal. Most people use gold to inject or extract holes from semiconducting polymers in electrolytes. And this turns out to be a fairly lucky coincidence that gold has a work function that aligns reasonably well with the highest occupied molecular orbital of most p-type semiconductors. So injection of charge is rather facile, of electronic charge is rather facile. However, if you push it a bit and start looking at systems where the highest occupied molecular orbital is low lying, then gold doesn't make a good contact. And then you see major changes in the electrochemical impedance behavior and the CV. If you change the metal electrode, if you go from gold to platinum, for example, you get major differences in electrochemical behavior that are currently not understood, cannot be accounted for using the traditional framework that we have for discussing these devices. With this model that I presented, it's very easy to account for and capture this phenomena.
Okay, thanks, George. Lauren, was there any other questions?
Yes, we just got a question from Drew through the chat. Would you like me to read that out to you, George?
I'm trying to see, I can see the participants list. Let me see the chat. If I can see the chat, then I can answer directly chat. Here it is. Hey, yes. Hi, Drew, thank you. General concept of oxidizing. So you gave the general concept of oxidizing P-dot, where holes inject from the electrode and ions diffuse in from the electrolyte. And they're electrostatically balanced with each other. But what happens in the reverse case? Hold on, this is scrolling while I'm reading. When P-dot is reduced, PSS is immobile, so cations diffuse in. But what happens with dopants such as tosylate? So, and thank you, Drew, for the question. So when P-dot is reduced, what happens is, this is the moving front experiment where you can inject cations into the film. They will compensate the anions of PSS. while holes are extracted from the back metal contact. And the motion of the ions is in this case by drift, because you create a field as you de-dope the P dot that basically helps cations, injected cations, transport through drift inside the sample. Now, in the case where you have mobile dopants such as tosylate, the whole situation can also be described with drift diffusion equations. You would just have to account for the fact that your compensating anion can also move. You would have to assign a mobility to that. And you end up having very important, very interesting phenomena where, for example, as you are injecting a cation, an anion might come off, or when you're injecting holes, back when you're de-doping, back when you're doping the material, the compensating anions can redistribute inside the material to respond to this hole flux. So I have a very simple MATLAB model that captures this phenomena, and I could send you some snapshots of characteristic behaviors of what happens when the dopants also move.
Yeah, thanks, George. There's also, is that a question there from Vinny? Maybe we could pick that one.
Yeah, the electrolytes you talked about in the last talk. Yes, we use aqueous electrolytes for bioelectronics in general. Usually it's when we look at the data that I showed with PDOT was with sodium chloride in water. For some other experiments, we might need ionic liquids or other electrolytes with a larger electrochemical window so that allows us to look over a broader range of what happens. This is certainly the case with the materials that have a low-lying HOMO that I mentioned earlier. There we look at non-aqueous electrolytes because of their electrochemical window. Now, the modeling that we do is purely electrostatic. It just captures the electrostatics of the problem and neglects a lot of the fine molecular level detail. So it's a phenomenological model that has, obviously, as every model, its limitations. It just captures the electrostatics of the problem. But often in these systems, the electrostatic forces are the ones that dominate behavior. Certainly the case with doping phenomena in semiconductors in general. So you can treat a lot of molecular level details by using second order corrections. For example, what is the field dependence of mobility or the field dependence of injection? If you use different ions, they would have different mobilities. They might experience different injection barriers. That's how you would capture some of the molecular level detail in this framework.
Thanks, George. I'm just going to flick, there's a few questions up here, but I'm just going to do one more, and I'll read it out, George. It's from Dan Lee. George, does the pore structure of PDOT affect the capacitive behavior? For carbon-based materials, it does, but how about in the case of PDOT?
So, thank you. PDOT, we don't, so there are different ways to talk about the material, and the notion of porosity or tortuosity that is used for some materials is not particularly fruitful in PDOT, because you can treat it in a continuous fashion. Ions would get in to the film and distribute uniformly down to very small voxels. So that means you can treat it as a slab of gel, if you wish, that has fairly uniform structure, again, down to this cubic micron. And you can assign a mobility to ions that ends up being fairly high. And when you manipulate the structure of P dot, for example, by ripening the P dot rich areas, then that mobility just decreases, the ion mobility decreases. That has been a good framework for understanding these materials. For other materials where you would have, for example, sintered titanium oxide particles, you can have ion transport in the space between these particles. There, using a uniform medium approach would not be fruitful. You would have to invoke the notion of porosity and tortuosity and all that.
Okay. Great, thanks, George. Look, there's a few other questions, but I'm sure George will get back to those and respond to you. So I'm just going to wrap it up. I'd like to thank, on behalf of all of you who attended, thank you for doing that. I'd like to thank George. As I said at the start, George has pioneered these fundamental insights into these types of materials, and you can see the implications of that knowledge in real applications. And I think the other thing out of George's talk today was the importance of being aware of emerging characterization tools in order to get those insights, and to sometimes look outside of our own fields for those characterization tools to gather that fundamental knowledge. So thanks again, George. Really appreciate you getting up a wee bit early over there in the UK. And on behalf of everyone, a huge thanks, and we'll hopefully catch up soon. Thank you.
Thank you. Thank you very much. Bye all. Bye.